Alright, so for our BME project, we created a heart rate monitor and pulse oximeter. This consists of three components: our Arduino, the breadboard, and the clip where the finger goes. In order to start collecting data, the user has to first insert their finger into the clip, and then once their finger is stabilized, they can press the run button in MATLAB. So first, the code will set up a connection with Arduino and it will start taking IR data. So while it is collecting IR data, you'll see a please wait, and this is when it's collecting the data. Next, it will go on to collect the red LED data, and as you can see, the peaks for the pulse oximeter IR data popped up. Now just wait until it finishes recording the red data. Once it's done with the red data, you can you can take your finger out of the clip, and here you can see that there are peaks for the red and IR data, which is a depiction of your heartbeat. Okay, so now that we know a little bit about the hardware, let's look at the code for taking heart rate data. So first, we have to let the computer know that we're using an Arduino connected to COM4, and our photo detector is plugged into pin A0, and our IR pin and red pin are connected to pins 2 and 3 respectively. Next, we're going to start with the IR LED. So first, we write a value of 1, which is a true, to the pin to turn on the IR LED, and we set the interval to be 1000, and let the time equal to 1 in the beginning. And so every time we take a new voltage reading, we're going to add 1 to time later in the code. We're going to display this recording IR data, and please wait, just so the user knows to let the user know that the computer is recording the data, and they should hold steady. So here's our for loop for collecting the data, and it's pretty much just a array that adds the voltage to the existing array every time a new data is collected. And then the elapsed time we use tick and tock to figure out how much time has elapsed. And after it's done collecting, it will display completed IR. So that's when the user knows that we are finished collecting the data for the IR light. And the code will then plot time versus the IR data. And next, after that, the user will see recording red data, and that's when it will record the red data. And the code is very similar, so we will keep going. And after that, the next plot we make is one of vlist, and we let vlist equal the red data, and we're gonna plot the red data with O's so that it's easier to see the each individual point. And then fs will be the length of time divided by the time that it takes to collect the red data. So this code, we brought it into class and we collected samples from many different students shown on the left here, and this is the data that we used for our project.
So for noise filter, here we just use a similar method, however it's not the exact noise filter. We name it because it looks better. However, it's a bandpass. So we're using bandpass we calculate the thing which have 50 beats per minute, and between 50 beats per minute and 220 beats per minute. So frequency 1 is 5/6 and frequency 2 is 12/6. It will make only pass a frequency which between these two frequency threshold. And the filter will fill the thing and give the figure. The figure will be looks perfectly smooth data. Okay, for the filter is see the filter here, because we find the first 280 data are super straight. we don't want that data. It's not the heart rate data, so we just get rid of them and plot the data, already filtered data. Yeah, it will look like very nice and heart rate data. So it goes to the next step. It was the precise raw data. And you can see it's the similar method we learned from the class at TSD. So this time we choose the 2N data. It will make the graph more have a better resolution. The thing we haven't got for during class is the X limited and things, because the heartbeat has to be from 0 to 220. So we just get the graph from 0 to 220, and the list is beats and PSD normal. So we sort all the PSD normal data, so we find which one is the largest. So I'm using this location to find the related bit and output the first highest and second highest bit, because sometimes we find it will be very close between the first one and the second one. So we maybe some noise or something else will change the data. However, it won't be a large thing. So we just output the both to compare to each other. If the data have a large gap, like the first one is a 198 and the second one is like 68 something, it shows like it's a wrong data. So we know we need to retake the data or have a better solution to precise the data. So that's all for our heart rate processing. After talking about how to collect the data, we collect over 50 students' data here. Because we import the time and save the code by writing like the student sample and the time, so it will be automatically to save the data by its collecting time. And for here, you can see we load one of data, and we can this data will have the large gap. You can see here. So we need a infrared gap filter. In the filter, for here, that you can write IR to red stand for infrared and red stand for write data. So just load the data. Okay. Go here. Here is a function to find the gap. We set the threshold at 0.2. You need to the code will minus the first value and second value, and take up the absolute value of the subtraction, and check whether or not it is larger than the threshold. After we find the gap location, we need to figure out is that the gap or is the outlier. So here's a method to check out is a gap or outlier, because if outlier, the two large values should be very small, like smaller than 10 location. So here's the NN is represent the list that contains all the location of outlier, and we check the new L is a list like the original new list minus the NN list. So we got the new list. The new list. It means that it will represent all the useful data for the gapping. So the method is minus the first the first value. There's first mean and the second mean. The first mean represent the thing between the large gap, the higher mean, and the second mean is the thing like under that, the lower mean. So we can get the difference between them. Because in this function we only have one gap, so we only need like new list 1, new list 2. Sometimes we may have two gaps, and in that time we need to make change. And here's how it works, and we can run the program and see.
Let's take a look at how to calculate the oxygen saturation level in the blood. So first, we have to use a theory called Beer-Lambert's law. And what it uses is that it uses two different wavelengths. One is the red LED, and one wavelength is coming from the near-infrared LED. And here's a picture of Beer-Lambert's law. So Beer-Lambert's law can be simplified into an easier equation shown here. C naught here represents the amount of oxygenated hemoglobin, and CR represents the amount of reduced hemoglobin. So in theory, C naught plus CR should add up to 100%, and if we divide C naught by the sum by 100, then we will get the percent oxygen in the blood. R is another ratio that we need to use in order, that is in the equation to calculate SpO2, and R will be a function that is written in our code. So to calculate R, we use the function called rcalc. The inputs are I1, IN1, I2, and IN2. I1 represents the valley voltage of the red LED. IN1 is the peak voltage of the red LED. I2 is the valley voltage of the IR LED. And IN2 is the peak voltage of the IR. So in order to find R, we just use this equation shown here, and we are able to get the ratio. Okay, so putting everything that we looked at earlier together, we can now finally use MATLAB to calculate the SpO2. So first, we have to load a sample. I just chose a random one here just to show you. And next, we define our variables. Alpha is the extinction coefficient of various things at different wavelengths. So the wavelength of our red LED and our IR LED. So in order to find I1, IN1, I2, IN2, the hardest part is to get it to be accurate. So sometimes there will be a data that might be an outlier and it might be higher than everything else. If we simply just use max of the entire data, then we might get something that's incorrect. So in order to do this, we take the mean of the 5 closest values, and then we go through the entire data set, 1,000 points, and we find every single mean of 5 points. So, and then we store it into a new array. So that's what these two for loops are doing for the red LED and the IR LED. And then after that, we can now find the valley by taking the min of the mean vector, and the peak by taking the max of the mean vector. And this, we found, will give us a more accurate data. Next section, we calculate R using the function that we defined before, rcalc. Here it is again if you need to see it. And then after finding R, we can just simply plug it into the equation to find SaO2, which is the oxygen saturation level. And we also included this. This isn't completely necessary, but we just included it to find C naught and CR.
So now we let MATLAB run the script that we have written to calculate the blood oxygen saturation. And for the data that we have received for this particular sample, the saturation is 98.47%.